All right, what has Sabine worked up today? Cosmology crises are only getting worse. Tell me, Sabine.
Any crises in cosmology now. I could talk about a new crisis development every day,
All
but
right,
that'll get tedious very quickly. So instead, I have a
okay.
quick rundown with the biggest crises that you need to know about, including the most recent twists and
Hey, you should do crisis of the week, just like zombie kill of the week, you know?
turns. The most reported crisis has been the Hubble tension. That's a discrepancy between different measurements for the value of the Hubble constant, one of the parameters in the current standard model of cosmology, also known
Right,
as lambda CDM. The data from
right,
the early universe, like the cosmic microwave background, gives a smaller value than those from nearby later data, like
right,
quasars or supernovae. And as the data
right.
have become better, the discrepancy has grown, not gone
Okay, yeah,
away.
okay.
The newest development is that we're now officially allowed to call it a crisis after the lead author of a recent study, Dan Skolnick, declared that the tension now turns into a crisis.
And it's called attention because the Hubble constant. So I think the idea was that the Hubble constant, which it relates to the expansion of the universe, changes with time, which means that it's not just expanding or accelerating at a constant rate, it accelerates at different rates. So why is this? And The reason why it's a crisis is because in order to explain that, they need a fudge factor term called dark energy that can model why it's expanding at an accelerating rate. So it's accelerating at an accelerating rate. Like that. That's what I understand up to this point. Maybe I'm right. Maybe I'm wrong. Let's see what Sabine has to say.
Finally, I've been wanting to use my in case of cosmological crisis break glass emergency kit for years. Last year, I told you that the tension was somewhat alleviated
Oh yeah.
by a study from the group of Wendy Friedman. It suggested that using data from the James Webb Telescope to
Right.
readjust the measurements from the later universe, the result was compatible with that from the early universe. Already back then, New Scientist quoted the above mentioned Dan's
What? What? She just said the opposite, right?
later universe, the result scope to Riemann. It suggested that using data from the James Webb Telescope to
Right.
readjust the measurements from the later universe, the result was compatible with that from the early universe. Already back then, New Scientist quoted the above mentioned Dan Skolnick with saying that this doesn't feel like the current state we're in. In his recent paper, he's
What?
basically made sure to bring the Hubble tension back. His group made the most precise calibration ever of data from the late universe by exactly measuring the distance to a galaxy cluster called the Coma cluster. This
Right.
could have confirmed the Friedman result and made the tension go away. It didn't. The second crisis in cosmology is that the cosmological principle just isn't correct. This
So essentially, if I understand correctly, someone came and said like, "Oh, if I readjust certain things, then there's no tension, which is there's no change in the expansion, and so we don't need dark energy, so we can forget that." And this group went and did even more sensitive experiments and said, "No, the tension is still there." So I'm thinking this has to do with dark energy, but let's see.
principle assumes that the universe is on average the same everywhere, and it's one of the assumptions for the current standard model for cosmology. Indeed,
Right.
we can use this model to calculate just how large the biggest clumps of matter should be. The trouble is that
How
astrophysicists
large the biggest chunks of matter? Wait, so when we read the cosmic background radiation, wherever from Earth, wherever we look, it's the same. And based on that, the assumption is that when the Big Bang happened, it was all uniform and homogeneous. So the overriding theory was that the universe expanded uniformly, and all of our models are based on that. But I did see that let's continue.
keep finding clumps that are bigger than they should be. There is, for example, the Great
Okay.
Wall, a collection of galaxies about 1 billion light years away from us that extends over 1.5 billion light years. The huge quasar group, which spans 4 billion light years, and then the recently discovered big ring that also spans 1 billion light years. If our
Okay.
theories were correct, then these
Right.
large structures shouldn't exist.
Should not
Another
exist.
piece of evidence against the cosmological principle is a discrepancy between two measurements of our own motion through the universe. You can
Okay.
do this either by measuring our motion against the cosmic microwave background or by using our
Okay.
motion against the average motion of distant quasars. This is
Okay.
related to the cosmological principle because to infer our own motion against the quasars, you need to know at what distance they'll be averagely distributed. The standard
Right.
cosmological model tells you what this distance is. But if you use that, then these two measurements of our own motion disagree by almost 5 sigma. These
Oh
two
my God, let me
at
look at that.
what
What?
distance
Okay,
they'll
yeah.
be averagely distributed. The standard cosmological
Right, so all she's saying is that even if you want to measure the rate at which you're moving using quasars, you need a model that estimates what the average quasar distribution would be to get an accurate measurement. And then over here you have, this is theory, this is measurement. There are no axes over here. It would have been great if Sabine had spent just one extra minute on this one, on this one video. So megaparsecs, so this is speed. So I don't know what she's looking at over here.
model tells you what this distance is. But if you
What this distance is, the cosmological model tells you what this distance is. The average distance between quasars. So the theory says it should be like that. That should be the average distance between quasars. But when we look, the average distance between quasars is actually larger. So again, our theories are not matching. Our theories are very good. We did a good job. It's like being 100, 150 years ago, 100 years ago, and being upset at Newton, like, oh, you give us crap theories. No, it's a good theory for what we have, our experimental evidence. It's great. We move forward. Just the same way the models that we have are very good. We're able to actually make, comparisons, but, there are discrepancies. And we're getting to a stage now where, we need to rethink a lot of things.
use that, then these two measurements of our own motion disagree by almost 5 sigma.
So essentially the two different ways of measuring a motion using the cosmic background radiation and using quasars, they are off by almost 6 standard deviations. So that's significant, but yeah.
The third crisis is that the James Webb Telescope has discovered big galaxies that were around when the universe was only a few 100 million years old.
Oh.
These galaxies appear surprisingly massive and mature for their age. It's like you finally got to meet your 2-year-old nephew, but he's 6'3" with a beard. Somewhat surprising. Some of these galaxies even exhibit features like rotating disks, which were not expected to have formed so early. This is why you have seen countless headlines saying that these galaxies shouldn't exist. As we discussed in an earlier video, this was
again, this is good news. This is good news. Whenever you're in a period of time where your models are breaking down with respect to your data, it means that your technology has gotten to a point and sophistication where you now need to go back to your models and come up with new underlying physics. And usually that paradigm shift will lead to even better technology. So it's exciting. This is exciting results, but you have to push. So what Sabine is doing, push and challenge and be like, no. That's how you leave space. You create space for relativity and things like that. Is by creating these rooms and pushing and saying, pushing back and being like, no, there's something else going on here.
was a prediction of modified Newtonian dynamics, but astrophysicists have trouble accepting this explanation. They've
well, let me go back. So again, here's the paper. Ultraviolet mass is at this, and then this is the speed, the phase. It's what. So dark matter prediction is down here. Data is up here. So even with dark matter, it's not. Let me go back. What is she talking
earlier I
about?
expected to have formed so early. This
Right.
is why you have seen countless headlines saying that these galaxies shouldn't exist. As
Okay.
we discussed in an earlier video, this was a prediction of modified Newtonian dynamics, but astrophysicists have trouble accepting this explanation. They've since proposed multiple alternative explanations that fit the cosmological standard model with dark matter.
Fit the cosmological with dark matter. So she's saying a modified Newtonian mechanics. So modified Newtonian mechanics, okay? Efficient formation of massive galaxy at cosmic dawn by feedback-free starbursts and stuff, okay?
You can tell that this is a crisis just by noting that they came up with these explanations after the
After something, dusty wind, clear web, super early galaxy. Dusty wind, clear.
data came in. By the way, this video comes with a quiz that lets you check how much you remember. And the
I don't
fourth
remember
and
anything.
final crisis is the sigma 8 crisis. This is
Right.
another discrepancy between measurements from the early and late universe, but this one is about a parameter, that's the sigma 8, which
Right.
measures how much matter clumps over time. Basically, it hasn't been clumping enough. The interesting thing about all these crises in cosmology is that they only came into focus in the past 10 years or so. A development that's been entirely driven by data. It hasn't
Right.
yet caused a major paradigm shift because
Right,
for
yeah.
99% of our observations, the standard model works. But
Pretty
that's like when a company says their update is 99% compatible with the previous version.
Yeah.
It's that remaining 1% that you need to
Yes.
pay attention to.
The last 1% makes all the difference in the world.
To me, science is more than a profession. It's a way to understand the
Okay.
world and how
Yeah.
to solve problems. This is
You're
why I'm
solving- Okay, brilliant. Yeah, I like the idea of Brilliant. It's a great platform. Yeah, let me just think about this. So all of these crises and like ongoing debates and whether dark matter exists or not. So yeah, the fact that there is this like online discussion and what is dark matter? How do we explain it? From my point of view, dark matter was always this fudge factor that's sort of holding your model together, much in the same way that when Planck quantized the black body radiation, it was just, it fits, but it opens the door to more underlying physics and underlying physical intuition. So the same way all of these errors now, that this last 1%, because again, back in the day, 100 years ago, the ultraviolet catastrophe, physicists, a lot of them were saying the same thing. We mostly understood everything. It's just this little 1%, we put a little fudge factor here or something. I'm sure we'll explain it in conventional terms. And it required a whole paradigm shift in order to fill in the gaps. So there's a lot that we do see. We have observed black holes. So singularities do exist. We observe them through the bending of light and the lensing effects. And recently they also measured the Hawking radiation using very sensitive measurements. So like she said, it is 99% explained. So it doesn't mean that all of physics and all of science is garbage. That's not true at all. But we need to focus in on that 1% indicates that there is deeper underlying physics that we should explore. So super exciting results. This is super awesome. I'm so happy.